Our speaker today is Paweł Dłotko, and he will talk about feature extraction and visualization methods in TDA. Take it away.
Thank you, Teresa, and thank you to the whole AATRN team. It's a great pleasure to give the second talk in my career on the seminar. It's a pleasure and privilege. So I will fire away. And I will tell you a little bit about the philosophy and the work we are doing in the center. I am developing in Poland with a group of fantastic people that I will introduce at the end of the talk. Let me start with a somewhat provocative question. Why we are doing what we are doing? And for me, one of the motivations, mainly also because I'm right now in the conference of statisticians, the motivation is coming from statistics. So what we see over there is a classical example from 1973 by Hans Combes. We have 4 different point clouds, and we can clearly see that they are visually very different. However, if you compute so-called summary statistics, for instance, the mean value of the x-coordinate, mean value of the y-coordinate, the standard deviation on x or y coordinates, the correlation between x and y coordinates, or if you try to fit the linear regression, a line with a linear regression, you will essentially get the same values, regardless for which of the sample you do it. So, as Combe message was that you should always visualize your data. That example was actually carried over in roughly 10 years ago by Alberto Cairo with the Datasaurus dozen. So we have exactly the same idea. So very different visually point clouds with very, very similar. So exactly the same up to the second digit of precision summary statistics. So the message is, well, first of all, the original message of Hans Combes that we should not trust whatever statistics we are using. We should be trying to understand our data. And but there's also another message. So, namely, sometimes summary statistics is not sufficient, and we need a better statistics for our data. And I think TDA is answering both of those calls. So it provides different statistics that tell you something about the shape of the data, and it provides what I call the topological visualization tools. Okay, so to start, let's put it into the historical context. Let's take a look at the state of the art. So when it comes to new types of statistics, should of course think about persistent homology. So very standard picture, we are creating a filtration by placing a ball of a radius r centered in every point of our point cloud. And we let r grow from 0 to infinity or maybe to some limit radius. And for every intermediate radius, we are computing homology, and we are tracking the homology generators in different dimensions as they appear and disappear. And that gives us the persistence diagram, which we see on the right-hand side. It can be thought of as a statistics, a feature of the data that, by the way, very nicely can be used to recognize the examples from Hans Combes and to tell them apart. So a classical feature, classical new type of the statistic is persistent homology. And when it comes to topological visualization method, we can go back to the mapper algorithm, which starting from the point cloud on the left-hand side, using certain transformation, it creates an overlapping cover of the point cloud. And given this overlapping cover, we can create a one-dimensional nerve of that cover, namely a graph whose vertices corresponds to cover elements. And if the cover elements happen to have non-empty intersection, we put an edge between corresponding vertices. And in addition, if we have some function on the top of our points, classical example is maybe a survival on some genetic data, we can express, we can actually transfer it to the graph by aggregating the values of the function in every color element and display them in the form of a color of the graph. So those are the classical tools of feature extraction and visualization. What I want to speak about is something maybe not that popular, but also tools that have a potential. So I'll start with an idea based on the Euler characteristics and the generalization of Euler characteristics to multifiltration. What I'm going to show you in the second point is an application to the statistics, to solving very classical problem of goodness of fit in the statistics. So the first 2 points are about topological features, statistics of the data. And the last 2 points, ball mapper, I don't think I will get over there because I moved it to the extra slides, but I want to show you the cluster graph, which is an idea located in the topological visualization of the data. I'll try to mention some of the applications, but I will keep that restricted due to the time restrictions. I will be happy to discuss them later on. Okay, so let's start with the topological features. That's my work with Davide Gornari. And everything starts back in 1758. So historically, we know that Euler wasn't the first one who realized that if you take convex polygon and take the number of vertices of this polygon, subtract the number of edges and add the number of faces, you will always get 2. But it is attributed to Euler, and therefore this number is called an Euler characteristic. The fact that you will always get 2 is a consequence of the fact that every convex polygon have 1 connected component, 0 one-dimensional cycles, and 1 void, which is it bounds inside. So that's a very classical, I think it's one of the first non-trivial topological invariant, maybe just after the number of connected components. And so given a general cell complex or simplicial complex, we can just compute it by counting the number of simplices of the following dimensions multiplied by -1 to the dimension of the simplex. So there is no linear algebra, it's pure combinatorics. The Euler-Poincare formula gives us a relation to the Betti number. So equivalently, Euler characteristic can be expressed as an alternating sum of Betti numbers. And of course, it's weaker than persistent homology. Given persistent homology, you can extract Euler characteristics, but not the other way around. But what I want to propose is I want to propose to use it in the data analysis. And there are multiple reasons for that. I think I mentioned the first one, so it's very easy to compute. But there is another one. So Euler characteristic is around for many centuries. And if you actually look through the mathematics, you can find it in the very different branches of mathematics, appearing in differential geometry in terms of Gauss-Bonnet. Algebraic topology, you have Euler-Poincare that I just presented. In algebraic geometry, you have Riemann-Roche theorem. And there are many, many more cases, many more results in which Euler number is present. So unlike persistence diagrams, which are pretty new creation, Euler number is with us for a long time. And we can use it to actually prove something about our methods. And I will give you one example later on. Okay, so if we start, now let's take a filtration, so a nested sequence of either subspaces of complexes, and use the Euler characteristic to characterize every step in the filtration. So over here, perhaps it's hard to see, but we have a collection of points sampled from a unit circle over here. And once again, in the standard way, we are placing a ball over radius r and let r grow. And for any intermediate radius, we are computing the Euler characteristics, and that gives us the curve that we see right here. So the idea is to use this curve as a functional feature of this point cloud. And here's the curiosity. So looking at this picture, you should be able to realize that we used Vittori-Rieb's complex in this construction. I'm not going to tell you why, you can ask me later, but if you can figure it out, figure it out. But the idea is to use Euler characteristic as a feature of the data. So it has been used multiple times in the history of topological data analysis community. However, for a long time, people consider it a kind of inferior because they believed that it lacks the robustness or the stability property. In order to speak about the stability, let me remind you what it is in the terms of standard persistent homology. So let me explain what happens over here, starting from the left picture over here. So on the left picture, we have 2 point clouds. One is denoted with blue, and the other is orange. And the blue points are sampled very nicely uniformly on the unit circle, and the orange point cloud is just a perturbed version of the blue point cloud. On the right-hand side, we have persistence diagrams corresponding to the blue and orange point clouds. And we also have the matching. I think this is one Wasserstein matching. And the stability result of persistent homology allows us to relate the amount of perturbation we did to the point cloud to the distance between persistence diagrams. And essentially, simply speaking, the stability, the robustness of persistence diagram ensure that if your data are perturbed by a little bit, then the resulting persistence diagram will also change by a tiny bit. Actually, it turns out that the same stability property holds for the Euler characteristics. So over here we have 2 Euler characteristic curves obtained exactly for the 2 point clouds that we've seen on the previous slide. So for the 2 point clouds on the left-hand side over here. And as you see, both of them kind of have this flat plateau over here on the value of Euler characteristic 0, which is an evidence which allows us to conclude that we are sampling from something with H1, so the first homology equal 0. And it's actually surprisingly easy to prove the stability result in terms of L1 distance, so a standard integral distance of the Euler characteristic curve that is bounded by the alternating sum of the one Wasserstein distance between the diagrams. So Euler characteristic curves are stable and therefore can be also used as a robust tool in the data analysis. So that's one good thing about them. But there are more. They are very easy to compute. So in computer science, we say that computations is embarrassingly parallel. So you have a very huge point cloud. What you can do is to construct your complex locally. And if you make sure that you don't double count your simplices, you can do your computation in totally distributed way without servers needing to communicate and still get the good results. So Davide did a prototype implementation, and we were able easily to get like 2 orders of magnitude above what persistent homology can do. And under some nice uniformity assumptions, essentially the sky is the limit, because again, this thing is embarrassingly parallel. It's stable, but there is also one more good news about the multifiltrations. So, as you know, multidimensional persistence is a big thing. This is something that we need. Unfortunately, it's very difficult because of inherited difficulties in mathematics behind it. The question is, can we use the Euler characteristics to understand multifiltrations? And in order to answer this question, let's think again what an Euler characteristic curve is. So what I'm claiming is that it is a sum of indicator functions of simplices. So once we have a simplex S that is born with the filtration value f of s, then the contribution of a simplex S to the Euler characteristic curve is the Heaviside function, which is equal 0 below the value of the filtration. So the simplex is not present before. But once it enters the filtration, it stays over there. It is equal 1. So we take this Heaviside function, we multiply it by -1 to the dimension of our simplex. And if we take those indicator functions multiplied by -1 to the dimension, sum it up across all the simplices in our complex, we get the Euler characteristic curve. And now the question is, what would happen if this filtration is not real value, but a vector value function? And if you think about it for a second, you realize that not much change. So the only thing that we need to figure out is what's the correspondence of the step function, of the Heaviside function for multifiltration. So over here, I have an example of two critical bifiltration. It means that our simplex S appear in two non-comparable values, I1 and I2 of the multifiltration. And then our Heaviside function is equal to 1 for any point which is greater or equal lexicographically to either of those numbers. And it is 0 otherwise. And then the procedure is exactly the same. We take this step function, multiply by -1 to the dimension of the simplex, and sum up over all the simplices. This way, we are getting something which we call the Euler characteristic profile. And let me show you one example. Again, in the interest of time, I want to just show one. Actually, two. So this one is a very standard example in TDA to show that we need multidimensional persistence. On the left-hand side, we have points sampled roughly from a unit circle. On the right-hand side, we have the same point cloud, but it is corrupted with uniform noise. And if you think about it, this uniform noise is effectively killing our homology, because in order to kill this cycle, you really need to get to the radius where you are starting to have simplices like those. But you know, those points of the lower density, they allow us to kill the cycle much quicker. And therefore, we won't be able to see the characteristic one point sticking out from the diagonal in the persistence diagram on the right-hand side. So the idea is to actually let those points which are sitting in the middle enter the filtration later. And in order to control when they are entering the filtration, we are using this second parameter, which is distance to the cave nearest neighbor. So on the high density region of your point cloud, the distance to the cave nearest neighbor will be small. Your neighbors are close. You are in high density region, so those points will enter quickly. But once we have the points in the middle, they will enter pretty late because this is the low density noise. So I have those two cases, and here are the corresponding Euler characteristic profile. So again, the signature of a cycle is the Euler characteristic 0, and in the clean case, we see it over here. So that's a clear evidence that we are dealing with a cycle. But even in the noise corrupted case, there is quite a large region of of our radius codensity bifiltration, where we can see the Euler characteristic equal to the Euler characteristics of a cycle. So over here, they are just marked where it is equal 0 and where it is different from 0. But also in the right-hand side case, we may be able to convince ourselves that we are dealing with a cycle corrupted with a certain type of noise. So that's one toy example. Let me give you another toy example. I won't have time to give more, but I will be happy to talk about them later. So over here we have an example of filtration with the values in three-dimensional space. RGB or red, green, blue is, of course, taken from a standard filtration of digital images. So we have filtration by colors. And in the simple example, we introduced two different patterns. The one on the top row we called stripes, and the one on the bottom row we call the tartans. So for each of them, we can create the Euler characteristic profile, which will be a function from R3 into R. And then we can compute the distances, mutual distances between all of those, which is the distance matrix on the right. So let me zoom it up. And as you see, those stripes and tartans, they cluster as you expect. So first of all, we have one cluster corresponding to stripes, one cluster corresponding to tartans, and those clusters are pretty far away, as we can see over here. I want to bring to your attention, for instance, this region right here. So it corresponds to a distance between the red stripe and red tartan, which is closer than distance between the red stripe and the blue stripe and the red stripe and the green stripe. So we have something that behaves reasonably, and we actually show, in the original paper, we show that on many different examples, it actually behaves properly and allows to deal with multifiltrations in some way, in some efficient way. We also shown some sort of stability property. Unfortunately, it cannot be expressed in terms of some sort of Wasserstein distance. We thought a little bit about matching distance, but we haven't found. But there is an obvious geometrical stability attached to those profiles as well. So this tool is also robust and can be used to process multifiltrations. Okay, you can play with the code. You can play with all the examples I showed and many more. So that's about the Euler curves and profiles. Now I want to show you how they can be used in standard statistics. So that's joint work with Niklas, Rafał, and Łukasz. And in this work, we are considering a very standard task in statistics, which is the goodness of fit test. So let me remind you what it is. So essentially, we have either one sample or two sample problem. In this talk, I'll focus on the one sample, but everything I say also kind of work for a two sample problem. So in one sample problem, you have a collection of points and a cumulative distribution function. And we are asking the question, does this collection of points follow the cumulative distribution function or not? In order to answer this, we are stating the null hypothesis, H0, which is that the collection of points follow the distribution. The alternative hypothesis, H1, is the negation of H0, does not follow. Two samples is very similar, but we have two samples. We do not have a cumulative distribution function. And if you want to solve this problem, a lot depends on this number over here on the dimension D. So if D is equal 1, then you have a lot of tools coming from the standard statistics. So I will only mention Kolmogorov-Smirnov test, which is the most standard thing because it kind of serves as inspiration for us. I'll mention it in the second. As your dimension is growing, so for two-dimensional case, you still have Kolmogorov-Smirnov and Kramer-Formises, which is let's say, a version of Kolmogorov-Smirnov. But the availability of tests is decreasing very quickly with the dimension. And that's oftentimes problematic because we are often dealing with a high-dimensional point cloud. Let me mention the Kolmogorov-Smirnov test. So over here we have, so that's the idea over here. We have a cumulative distribution function, which is the nice, smooth red curve. And we are building an empirical distribution function based on our sample, which is the blue curve. And the value of the statistic is just L infinity distance between those functions. And the magic of Kolmogorov-Smirnov is that no matter which distribution you are using, what does it mean if the distance is large or small? It's actually given to you in the statistical tables. You can open the table and you know that this value, whatever it is, on the confidence level, say 0.05, allows you to reject or do not allow you to reject the null hypothesis. So there is something universal about the Kolmogorov-Smirnov. The problem with generalization of this technique to higher dimension is actually the fact that you need to consider all possible permutations of axes in order to in construction of this empirical and continuous cumulative distribution functions, essentially to capture the correlation patterns. And this is actually what kills the complexity. So our idea is to replace the cumulative distribution functions with some topological invariants. And because I'm speaking to you about Euler characteristic for the last 20 minutes, you can immediately realize that I'm going to put an Euler characteristic over here. So the topological testing, they work in the 3 steps. So again, we are in the standard setup of one sample test. So we have a cumulative distribution function f, and we have a sample. In the first step, we want to understand what is the expected Euler characteristic curve of the sample of the size n sampled from this cumulative distribution function. In order to get it, we are sampling some number of point clouds. For each of them, we compute the Euler characteristic curve and we average them. So that's our blueprint. This is the expected average Euler characteristic curve of the point cloud of the size n. In the second step, we need to understand what's the standard deviation. So how far away points sampled from f can be. And once again, we are doing it in very obvious way. So we are sampling some more point clouds, and we are checking what is the standard deviation. Essentially, we are taking the quantize and the level of 1 minus alpha of the distances we are getting. So this is a standard construction of this goodness of fit test. It actually will reject a correct hypothesis in alpha% of cases. That's the feature of the test. And in the last step, we are actually doing the testing. So we haven't touched our point cloud X so far. Now it's the time to actually get it to work. And the last step is pretty easy. So we compute the Euler characteristic curve of this point cloud X. We check the distance of this Euler characteristic curve to our blueprint, to the average Euler characteristic curve. If it is above the critical value, we can reject the null hypothesis. If it's not, we don't have a reason to reject. And over here on the right-hand side, we have a number of average Euler characteristic curves for some products of standard distributions. So they look a little bit different. What you need to be aware is that we are not actually checking the equality of the distributions, or we are checking the equality of the Euler characteristics. That raises the question when two distributions have the same Euler characteristic, and we have an answer to this thanks to Niklas and Tobias. So we understand when this test works. And because of the fact that we have a pretty good theoretical understanding of Euler characteristic, we are able to prove some limit behavior of the test. So in case when the number of points goes to infinity, we understand the process of the convergence to the expected Euler characteristic to the mean as the number of points goes to infinity. We are also able to estimate the probability of type 2 error, which is the failure of rejection of H0 when it should be rejected. And this thing is decaying exponentially with the number of points. So we are able to actually show some theoretical properties that shows that this test actually is doing what it's supposed to do. And of course, everything over here happens in the limit. We don't have any understanding of the finite case. When it comes to practical usability of this test, we are looking at the so-called test power, which is the probability that H0 is rejected when it should be rejected. And without spending too much time, we've done extensive Monte Carlo studies on this. We compared point clouds of very different distributions, and we present them in terms of this heat maps. So when you think about the definition of the test power, which is the probability that the null hypothesis should be rejected is rejected when it should be rejected, you want this probability to be as high as possible. In other words, with this color scale, you want to see as many yellow points or yellow squares in this matrix as possible. So what we see over here, this is a Kolmogorov-Smirnov test with 250 points from three-dimensional distribution with the average power of 80%. This is the topological test. So let me go back and forth. You see that the topological tests actually have, you can see that it has a significantly higher power. And over here we have, hold on. Over here we have the 5-dimensional point cloud with 500 points. So in this case, we didn't manage to finish the computations for Kolmogorov-Smirnov. Still, the topological tests have roughly 85% of power. So if you compute an average over this matrix, we could spend quite a lot of time trying to understand why some of the distributions are hard to tell apart, and the results kind of make sense. So there's a lot that we can kind of get out of those matrices. In addition, every good test should have the property that if you show it more points, it gives a better results, and this is also the case. So over here we just fixed one pair of distributions and sample more and more points, and on the y-axis we have the average power of the tests. In orange there is Kolmogorov-Smirnov. In the blue it's the topo test. So both of them are growing as we are showing it more and more points. Topo test is kind of always on the top to our competitor, which is the KS. So once again, there is a code available. You can, as every other code, you can pip install it. It actually performs very nice, even in dimension 1, which is quite surprising to me. We still beat the standard tests. But what I'm trying to do is to do practical stuff. And you can always ask the question, do I really need the cumulative distribution function? Because it's extremely improbable that a biologist will come to you with 5-dimensional point cloud and give you exactly the formula for the expected probability density from which it is sampled. It turns out that it is not always the case that you need this formula. Let me show you one example, which is based on the work on the damage identification with the topological testing. It's done with a group of people working in the mining department. So they're dealing with mining machines. So on the lower left corner, we see a crusher. That's a big machine that takes big rocks and the input, and it returns small rocks and the output. It crushes them, and when it crushes them, there is a lot of vibrations. And so they feed a lot of vibration sensors all around the machine. And the problem is when something gets broken, you get this cyclic impulse hidden in the signal. It's very much like you ride your bike and you hit a curb, and then you hear this periodic umbling. That's precisely what we want to detect. So the question is, can we use the machinery of the topological tests? Of course, we do not know what's the probability distribution from which it is sampled. But what we do know is we have a lot of historical data from this machine where it was actually working perfectly. And if you think about the construction of the topo tests, the only thing that we need to know, we need to be able to sample from the distribution. And we don't need to know the formula. You can sample from the distribution essentially by using the historical data. So over here, it's a very similar pipeline to the topo tests. The difference is we are not dealing with Euler characteristics, but we are dealing with the Tackelson bending theorem and the Betti curves instead of Euler characteristic curves, but the rest of the methodology is similar. And let me show you. So when you are working with engineers, there are 3 layers you need to cross in order to gain their trust. The first layer, we need to show in the theoretical model that the methods works well. And the theoretical model is so-called alpha stable noise, alpha stable distribution. It's a probability distribution that depends on the parameter alpha, which we have over here on the y-axis. For alpha equals 2, alpha stable distribution boils down to a Gaussian distribution. And as we move alpha to closer to 1, it becomes more and more impulsive. And on the x-axis, we have the amplitude of this cyclic impulse. So of course, the smaller the amplitude is, the more difficult it is to detect. And our main competitor in the state of the art is the so-called CVB method. It's a spectral method. The TDA test power is in the middle. And the difference is on the right-hand side. On average, topological methods performs better than the state of the art on the synthetic example. So that was the first layer of trust. Second layer of trust was on the test bench. So actually in the lab condition, they built this machine and they have an engine, so they could rotate on the different speed, and they have a broken and non-broken components. So over here, we couldn't done any Monte Carlo testing anymore. But what we did was to vectorize Betty curves and to separate them using SVM. So essentially separate them by a hyperplane. We got 100% separation. So on the right-hand side, you can see the PCA plots. So we project the Betty curves on the first two principal directions. And you can see that the broken and intact cases are kind of well separated, which also is an indication that the results of the classification are expected to be nice. And of course, the last layer is to actually show it in practice. So we have actually one of our collaborators registering, in this case, acoustic data from the Euler, so the acoustic data from the bearings. And the idea is to recognize which bearings are going to get broken pretty quickly. So those are industrial data, so whatever the results we get, there is a huge amount of noise. But again, TDA works better than the spectral methods, but the very good message is that if you combine them, you get even better results. So TDA is bringing something new to the table, something kind of orthogonal to the spectral methods, and this is what we see over here, and also in many other occasions. Okay, so I realized that I spent a lot of time talking, being left with 2 minutes to speak about topological visualization. Am I allowed to go over like 5 minutes more and kind of wrap it up in 7 minutes? Would that be okay, or would you like? Okay.
Yes.
I see Bastian saying yes. So let me tell you about the cluster graph very quickly. So there's Mapper. I like Ball Mapper because it's my baby. There's another thing which is called a cluster graph, and the idea is to take a huge amount of clustering algorithms and kind of put them into a graph so that we know what the layout of the thing is. On the left-hand side, we have 2 different point clouds. And looking at this, we can agree that there are 4 clusters in both cases. But the geometrical layout of those 4 clusters is very different. And clustering algorithms will not give us this information. So what we want to do is to put on the top of the clusters some extra metric information. So in this case, we are taking our clusters and we want to define a distance between clusters, for instance, by taking the maximum, minimum, average distance between points in the 2 clusters, maybe Wasserstein distance between them, so that we get a distance between every pair of clusters. And in this case, after pruning some of the edges, we shall be able to see that the filtration of edges for those 2 cases are different. And therefore, even though both cases have 4 clusters, we are looking at something with different geometrical layout. And then we can start playing, as we can do with Mapper, with various real data sets. We can start to get pretty quickly a reasonable result. So this is just an example of quite standard 6-dimensional diabetics data set from which you can can show 3 different types of diabetics. But what we also need to do, especially in TDA, is to confront our competitors. And we do have very strong competitors, just those guys, to name a few. So let me start with a very simple example. So it's an artificial example. We took 2 lines which are orthogonal, but not touching each other in 500-dimensional space. And in addition to those 2 lines, far away from them, we actually sampled a number of points from a normal distribution, and we checked what we get from PCA. This is the left-hand side picture, UMAP. So PCA got the Gaussian as well, one of the lines, okay, and there is this second perpendicular line which we don't get over here. UMAP gets nicely the Gaussians, but totally mess up the lines. T-SNE, very much like UMAP, and the cluster graph on the left-hand side give us the structure. So that's one good indication. Let me also mention another aspect why. So all of those dimension reduction methods, they are trying to embed our point cloud into Euclidean space. Oftentimes, when we are dealing with metric data, this embedding is not possible. And the classical example is, the embedding of a Y-shaped graph. So if you have a graph like this, where the distance of the central points to the endpoints is 1, and the distance between every pair of points from the endpoints is 2. This graph doesn't have an isometric embedding to any Rn, no matter how high the R is. So if we actually put some more points and try to do UMAP, T-SNE, or fade, UMAP mess up totally. T-SNE or fade, they're providing the embeddings with minimal distortion, but still they're messing up the distances, while the cluster graph, because it computes the distances in the ambient metric space, it gives the distances as the labels of the edges in the correct way. So sometimes actually not needing to embed the things into Euclidean space but it is useful. Then let me mention one more thing pretty quickly. So very often when we speak about mapper, we are waving our hands a lot, trying to claim that the thing looks like the real data. And there are a number of nice theorems saying that if you sample enough points, then this thing is converging to a rep graph, and with this or that type of the convergence. However, the problem is when I'm speaking to my friends in biology or social sciences, that they kind of refuse to give me infinitely many points. So what we need is some sort of quality measure for the point clouds we have. And as a part of this work, we are also proposing a quality measure. Let me briefly discuss it, and that should actually wrap it up. So we are working under the manifold hypothesis, assuming that our point cloud is sampled from a manifold. We can estimate the geodesic on the manifold using the k-nearest neighbor graph and the shortest path algorithm on this k-nearest neighbor graph. So we have an estimation of the intrinsic distance on the point cloud. If you think about it, cluster graph also gives you a sort of distance between points. So if 2 points are in the same cluster, the distance is 0. But if 2 points are in different clusters, we can also do the shortest path business, and we can check what's the distance between 2 points in the cluster graph. And the question is, what's the correspondence between the KNN, the estimator of the intrinsic distance, and the cluster graph distance? And what we are proposing is to use this ratio as a quality measure, so the metric distortion as the quality measure. So I'll be skipping the details in order to save time for the discussion, but we decided to take a look of the absolute value of the logarithm of the ratio. Essentially, it is because, well, we want to keep the error. We want to look at the order of magnitude of the error, no matter which one is greater and which one is smaller. And this metric distortion is important because it gives us a way to prune some of the edges, but it also gives us a quality measure of the resulted cluster graph. It allows us to say how accurate it is to recover the metric structure of our data. About the pruning, if we look at the bottom of the page, we have the clustering of this half moon dataset with 10 cluster, I think, using k-means. And at the certain stage of the pruning, if we still have this edge we realize that this edge will have very high metric distortion because the intrinsic distance, we really need to go around the whole thing. And this edge over here is a shortcut. And therefore, this number, this metric distortion will be very high for this edge. And therefore, we have a reason to remove it, to prune it. And once we do all the pruning, we have something that represents as accurately as possible the metric structure of our data in the form of a graph, very much like a mapper graph. So I'll just skip the thing, and again, there is a software which is pip installable, and the whole idea over here is to build something taking an advantage of the vast collection of the clustering methods. So I'll be wrapping up. Recently I wrote 2 popular science articles. This one is about the feature extraction in the European Mathematical Society magazine. This one is about the visualization methods. So this one is mostly about the ball mapper in various applications. And let me thank all my students, postdocs, external members of the group, visiting sabbatical professors, etc. It's great to be part of such a fantastic team, and everything I spoke about, everything I did is mostly thanks to those people over here. Thanks to our sponsors, the Dioscuri program, and sorry for going over time. Thank you very much for your attention.
Thank you very much for this very interesting talk. Let's please all unmute ourselves so that we can clap together. Great. Does anyone have a question? Yeah, Bastian.
I would start with one. Thank you so much, Paweł. That was wonderful. I really like the way you outline things. In particular, what has TDA ever done for us, right?
That was not the Python, but
yes,
I wasn't
yes.
brave enough to put the
no.
pictures.
I imagine it, right? But what did it do recently, right? But I had a minor technical question. So you also mentioned, I think, the ECPs, right? So the profiles which can work in the multifiltration setting. So I know a little bit about some work on Euler characteristic surfaces.
Yeah.
Is the main difference that your method subsumes the other one in the sense that it also that it doesn't need any discretization and binning? Did I get that right?
Yeah.
Is it more general? Okay.
Yeah, so it doesn't need any discretization, and we also have this sort of stability results in this case, because for the other surfaces, what you are doing is when you have a bifiltration, you are computing the value of the Euler characteristic on a uniform grid of points, which is an obvious. So that thing is just a generalization of this concept. But in a way, it seems more natural to do it this way. If you really think about how it generalized from one-dimensional Heaviside function to higher dimensional Heaviside function, we kind of spell it out in details, this part.
Yeah, no, I really like this.
Some ideas were flying around before.
Yeah.
Absolutely.
Oh yeah, no. I mean, this is really more for me to like put these puzzle pieces together, because I think this formulation is honestly way more elegant. So thanks a lot. So.
Thank you. Who wants to ask the next question? Junyan?
Hi. Thank you for the talk. I have 2 questions. So you in your topo tests, could you clarify what your null hypothesis is? Is it just that the 2 distributions have the 2 samples have the same distribution, or the distributions have the same topology, whatever that means?
Yeah. So actually, if you want to be totally rigorous, we are testing if they have the same Euler characteristics. So this is the null hypothesis, and if you want to understand which distributions have the same expected Euler characteristic, I think Niklas is on the audience, one of the author of this work. However, again, it's really hard. So if you know how to find examples of two different distributions that have the same Euler characteristic, you will find them. But let's say they're not present in nature. But we are really testing the hypothesis that they have the same expected Euler characteristic. So that was your first question, but you had the second one, and I'm not sure if I didn't get it.
Yes, I haven't mentioned the second question. Yeah.
Okay, does it answer your first one?
Yeah. So you're saying that you're working on the Euler characteristic level, but very rarely do you see like two distributions having the same Euler characteristic.
That's correct.
Okay. My second question is, so you mentioned that for your rock-like example, your broken machine example, you mentioned that generally TDA works better than the spectral methods. Do you have any intuition like why this is the case? Because it seems that if your frequency is pretty stable, like the spectral methods should work pretty well.
Yeah, so the short answer is I do not know. But if you look at the signal, so we have those examples of the signal over here. It's not that we are looking at some nice and smooth sinusoid. So those impulses are really coming from, when a big rock comes in, everything is shaking, and and you get this high impulses. So that is something that potentially may cause a problem, and then they kind of come in the random time steps. So a priori, I do not see why. I do not see a clear advantage for spectral methods. But to be fair, I don't know the answer to your question. So what is the methodological reason why TDA may potentially be better? That I do not know. Keep in mind what we have over here. So the fact that combining them together actually is even better than every single one of them. I do not have a good explanation for that. Let's state it as a fact. Sorry.
I see. Well, it's still nice that we get better results here. Thank you.
Thank you.
Okay, any other question? Maybe while people are thinking about their question, I want to just point out that in the same ATRN channel, we also had a talk quite precisely a year ago by Niklas about the topo test. So if you're interested about that, you can also watch a full hour talk or 50-minute talk about that. It's on YouTube. Okay. Did anyone come up with a question in the meantime?
So either it was very clear or very boring.
I think it was very clear. Yeah, I was thinking about questions during the talk, but like many of them you then already answered yourself. Yeah, maybe let's end the recorded part here then, because we anyway are already a bit over time, and then people can still ask questions after the recording is stopped. Thank you again. It was a great talk.
Thank you so much for having me.